Alright, this video is about the combined gas law, and it's going to be a little bit about Charles and Boyle's law as well. The combined gas law is right here in front of you. You can see that it's P1V1 over T1 is equal to P2V2 over T2, and I have labeled out to the side what each of the variables stand for. I've also included the units. The unit of pressure could be ATMs, atmospheres, mmHg, or millimeters of mercury, or kPa, which is kilopascals. Volume usually is in liters. It can be in milliliters, but I have to have both sides be in the same thing. So if this is in milliliters, this has to be milliliters as well. The same can be said for pressure. If I use pressure in atmospheres, then both of those pressures has to be in atmospheres, or both has to be in kilopascals, etc. And temperature absolutely has to be in Kelvin. It cannot be in Celsius. So on your reference table, you have a formula that tells you that in order to convert from Celsius to Kelvin, you add 273. So we'll be using that as we work these problems today. All right. I'm going to move down here and look for just a moment. The combined gas law is actually made up of three separate laws. We're going to look at two of them. One is Boyle's law, and Boyle's law basically takes temperature out of the above equation. So if I remove that with my fingers, you can see that I have the formula that's down here at the bottom, P1V1 equals P2V2. So Boyle's law relates pressure to volume. He describes what happens if the pressure goes up, what would happen to the volume. And if you can remember from math class, when things are multiplied, it makes an inverse relationship. So what that means is that when pressure goes up, then volume has to go down. Or if pressure goes down, volume has to go up. They have to do the opposite of each other. The other law that's a part of the combined gas law is called Charles's law. And I'm going to have to make the top one go off the screen here. Charles's law says V1 over T1 equals V2 over T2. And what he does is he takes pressure out. So up here above, if you could picture taking the pressure out of both of these and still being able to see the rest of it, I have V1 over T1 and V2 over T2. And if you can remember from math class as well, whenever you have something divided by something else, that makes a direct relationship, which means that if volume goes up, temperature has to go up as well. And if one goes down, the other one has to go down. They have to copy each other. So one of the things that I'm going to do is make another video that has working the problems with dummy numbers, because your state final exam loves to give you problems that don't really have many numbers to solve the problems with. They just ask a generic question. So look for that video about how to answer questions about what happens to the pressure if the volume is doubled or something along those lines. For now, we're going to work some problems that actually have to use the formula. So here we go. Here's our first one. Our steps to problem solving. Our first step is going to be to write down what you know. That's always going to be my recommendation, is to make a list. And right here it tells me that I have 1 liter of a gas. And I recognize liter as a unit of volume. So I have a V. And that gas is at standard temperature and pressure. Well, standard temperature, if I use my reference table, and if you're in my classes, then I've given you the reference table, on the front side of it, you have a little place that tells you standard pressure and standard temperature. And I have 4 standard pressures there that I can choose from in order to solve this. I'm just going to choose the 1 ATM because I like multiplying and dividing with ones. That's a pressure. The problem also says standard temperature, and standard temperature is 273 Kelvin. So there's my T. It says it is compressed. That means it's squished. It's squished down to 473 milliliters. Well, I know it's got the liter part in it, so that's another volume. But I see liters and I see milliliters over here. They have to be the same. I have to use the same units. And so I'm going to convert this to liters by dividing by 1,000, and I'm just going to take that out of it. So now I have 2 things in liters. And it wants to know the new pressure of the gas. It wants to know the pressure at that volume. It doesn't mention temperature. So what that means to me is the temperature is staying the same. So I have 2 choices. I can either put temperature over here, and I can put it in, and I can put it into my equation, or I can simply just strike through it, which is what I'm going to choose to do. If it doesn't change, I can take it out. Well, we're dealing with the equation that we had before. P1 V1 over T1 equals P2 V2 over T2. And we just said, life would be easier if we took the temp out. If the temp doesn't change, it can go away. That leaves me plugging in P1 V1 and P2 T2. I went ahead and set it up almost as if I had like a before and an after. Before, I have a liter and it's at this pressure. After, I squish it. Somehow I'm compressing it and pushing it together. What's its pressure going to be now? So it doesn't matter if these two numbers go on the one side or if they go on the two side. All that really matters is that they stay together. So I'm going to go ahead and put them on the first side, since that's where I have them, that I've got 1 liter times 1 atmosphere is equal to 0.473 liters times whatever my new pressure is. It also doesn't matter that the P was on the left side up here, but it's on the right side down here. It's kind of like saying 1 times 3 is the same thing as 3 times 1. It really doesn't matter as long as they stay together. And then what I need to do after that is I need to divide both sides by 0.473, and I will get a pressure as indicated up above. I do have the answer up there of 2.11. And if I'm confused about what units to put, when I divide both sides by 0.473, I also divide by liters, which means my liters are going to end up canceling out. My answer has to be in atmospheres. Alright, let's look at another problem. This one says the temperature inside my refrigerator is about 4 degrees Celsius. So I'm going to take this and I'm just going to kind of divide it up into two sides. I've got the inside my refrigerator. If I place a balloon in my fridge that initially has a temperature of 22 degrees. So basically we've got, we'll call it before and after. Before fridge and after fridge. So before the fridge, it says the balloon was 22.0 degrees Celsius. Well, if you remember from earlier, I told you that you cannot work these in anything but Kelvin. So you are going to have to add 273 to 22 to convert it. So that'll be 295 Kelvin. That's my temp. And it has a volume initially of 0.50 liters. And it says, what will be the volume when it's fully cooled by my fridge? So after I put it in the fridge, I'm going back up to the beginning now, where it says that my fridge is 4 degrees Celsius. And I'm going to have to know that when I put my balloon in my fridge, that it's going to become the temperature of the fridge. It's going to be 4 degrees Celsius. And if we convert that to Kelvin, we've got 277 Kelvin. And it wants to know what volume that will take up. It never mentions pressure. Pressure is never mentioned. The only formula that I really have that has these in there is the same one we worked with a while ago. P1 V1 over T1 equals P2 V2 over T2. And if pressure is never mentioned, we're going to take it out. What we're assuming is that it stays the same, it doesn't change. So that leaves me plugging in my volume over my temp. And again, it doesn't matter if the things on the left go on the left or the right down here as long as they stay together. So I'm going to plug in to my equation here. I'll scoot over just a little bit. I'm going to put in 0.50 liters over 295 Kelvin equals some other volume over 277 Kelvin. And then mathematically you're going to rearrange it, and you will end up with a volume of 0.47 liters. Now obviously I've already got the answers up there, so if you need to pause the video while you punch it into your calculator, make sure you get 0.47 liters. So we're going to go on to the next problem. Alright, we have one more problem here, and this problem is about the pressure of a gas and what it will be if the volume is changed and this time the temperature is changed too. So I'm still going to set myself up with kind of a before and after column. And so before, I'm going to say that I have a pressure of, of 5.5 liters of gas. The pressure of that is something else. The liters tells me it's volume. 5.5 liters of a gas. It is at 77 degrees Celsius or centigrade, which means that I have a temperature of 350 Kelvin. If you don't remember how to do that, remember I'm adding 273 to the Celsius to get here. And it tells me it has a pressure of 4.2 atmospheres. And they want to know, what will the pressure be? So the pressure is what I'm looking for. If the volume is decreased to 3.0 liters and the temperature is increased to 177, so that would become 450 Kelvin. So this time I have all of the pieces. The two problems I've worked before, I was able to take something out, but on this one I can't take anything out. My volumes are different, my temperatures are different, and I can't take out the pressure because this is what I'm seeking to find. So this time, when I put down my equation, I'm going to have to keep all of the pieces of it, and I'm going to have to plug them all in. So this time, I still have to keep everything that's together on one side together in my problem. So I'm going to put in 4.2 atmospheres, I lost my point, times my volume is 5.5 liters. That is over 350 Kelvin. It is equal to some pressure times 3.0 liters over 450 Kelvin. So from here, if you're having trouble with the math, simplify this side, multiply it by 450, and then ultimately divide by 3. I'm not going to carry out all of the mathematical steps of how to do that. When you solve for P, your answer that you will get should be 9.9 atmospheres. In the end, the kelvins will cancel, the liters will cancel, and I'm left with atmospheres as my unit, which makes sense because that measures pressure.